Let's now consider the effect of a polar aprotic solvent on the SN2 reaction. And we'll use DMSO, dimethyl sulfoxide, as our example. But the principle will apply equally to any of the other polar aprotic solvents. DMSO is closely related to acetone, but with a sulfur instead of like carbon, which means that it's a little bit less polar. Again, let's look at the reaction of iodomethane with a nucleophile. And this time, let's use potassium fluoride. So we'll use fluoride as our example. Mechanism will look like this. We'll have a transition state. There's a partial minus charge on the fluorine and a partial minus charge on the iodide. Done, we'll make fluoromethane. And the iodide. Once again, the energy diagram, a single step. Exothermic reaction. With just one transition state with partial charges. And what we want to do again is we want to think about how dimethyl sulfoxide is going to interact with the various species that are part of this reaction. Potassium ion, fluoride ion, iodomethane, and this transition state. Dimethyl sulfoxide, because the oxygen has a partial negative charge on it and is unhindered, is quite good at surrounding the potassium ion. So we will have potassium ion surrounded by partially negative oxygens, becoming significantly stabilized. We get a nice solvent shell with all these partially negative oxygens interacting with potassium. Unfortunately for fluoride ion, though, partially positive N, sulfur, is blocked by the sterically bulky methyl groups, which means that fluoride is going to be out here relatively unsolvated. So that's a leaking anion. It is a relatively good base because HF, even though it's not a strong acid, is not a particularly weak acid either, pKa in the 3 to 4 range. So fluoride is not particularly happy. Fluoride would have been happier if it was in a non-polar solvent, because in a non-polar solvent, at least potassium wouldn't be being solvated either. And so you could have this ion pairing effect where potassium and fluoride are kind of going together in the solvent. So in the unsolvated case, fluoride is significantly lower in energy than it is in the solvated case. What we're doing by removing removing the potassium, solvating the potassium and not solvating the fluoride ion, is we're actually raising the energy, lowering the energy of potassium, but that's not relevant because potassium ion is not actually part of the mechanism anyway. The most important effect is the increased energy of the fluoride ion because it's left all alone. Fluoride was invited to the prom by the potassium ion and thought that that was going to be great, it was going to have a great time, and then when potassium ion got left here all alone, no one to dance with, very unhappy, rising in energy. The fluoride ion here will also not be solvated effectively, but it won't care as much because now it's starting to bind to the partially positive carbon from the ion of methane, which means that it no longer has a full negative charge on it. It only has a partial negative charge, so the energy, though it will increase, it won't increase by as much. Because of Coulomb's law, a partial negative charge is going to be less unstable and less influenced by the ion dipole force than the full negative charge. It doesn't rise by as much as it did for the starting material. The iodide ion is less effectively solvated by DMSO than it would be in the absence of a solvent where it can interact with potassium. Because it's large, it doesn't really matter that much. Its energy rises, the activation energy. So if we look at the activation energies and compare them, it's significantly smaller than the activation energy in a nonpolar solvent or the absence of a solvent. And since we know that a lower activation energy is associated with solvated, the activation energy for DMSO is smaller, unsolved, sorry, yeah, smaller. So the SN2 reaction goes up. And polar equivalent solvent. Smaller activation energy for DMSO, larger rate for DMSO. That's the opposite effect that we saw for the protic solvent. You'll notice that in both Aprotic, the starting material changes by more than the energy of the transition state because the ions are in the starting material. And all solvents have a bigger effect on the ions than they do on the partial charges in the transition state. But the energies are going in the opposite direction. The energies that we saw for methanol, we would see that the energy drop for methanol was larger than the energy drop on the transition state. And so our graph looks more like that, as opposed to the graph that we saw for methanol DMSO, which means that the rate constant for methanol is smaller yet. Which means that the SN2 reaction is enhanced in a polar aprotic solvent. And if we want a reaction